Gaussian-Jordan method here. Yeah, that's the Gaussian elimination is where you just have the zeros cancel, and then you back solve. But when you solve for the identity matrix, that's the Jordan method.
All right, we're going to go ahead and get started. Okay. So, sort of picking up where we left off last time. Let me see if I've got my notes from last time that I can use. Yeah, I do. Okay. So last time we were in the middle of an example, and we left off. So we were doing this example. We were calculating the work done by a force for a particle moving from the origin to 1, 1 along 3 paths. All right? So we have done the first path, the second path, and we were working on the last path. And I'm just going to remind you that whenever this, well, I'll write out a reminder for you, because I do want to think about that a second time. So where we were here was we were evaluating this integral, and then I logged into Wolfram Alpha and put that integral in there. I think I completed that, didn't I? And get a result for that?
Yeah, but we ran out of time.
But we didn't write it down?
No.
So I'm just going to go ahead and tell you that that result was 1/2 times negative theta plus 4 sine theta minus 3 sine theta cosine theta. And that needed to be evaluated from 0 to pi over 2. Now, whenever this is the case, now and then you're going to look it up in a table. That's fine. Now and then you're going to use Wolfram Alpha. If you have used a reference, I need you to tell me that you've used a reference. So I would just say, I've used Wolfram Alpha here. Get that result. Okay? All right. So then I've got 1/2 times negative pi over 2 plus 4 times the sine of pi over 2, which is 1, minus 3 times the sine of pi over 2 cosine pi over 2, which is going to give me a 0, minus, well, in the case of 0, this is 0, sine theta, theta 0, sine theta 0, sine theta cosine theta 0. So all 3 terms for the case of 0. Okay. So I evaluate this. I've got 4 times 1 divided by 2, so that's 2, minus pi over 4. That's a good enough answer for me. I think your author went on and wrote that as 1.21 or something, but I'm fine with either of them. All right. So what I wanted you to get out of this example is the following. When we calculate work, we must do a line integral. In order to do a line integral, we generally have to, let's just remember for work, have the integral of f dot dl, where if L is a location of something, you can also call this f dot dr prime if you want to. I think, what have I been calling it in my previous notes? L or R? I was calling it R? Okay, that's fine. Dr, fine. And generally what you'll get from this is that you'll have to integrate from point 1 to point 2. And this is the work that's done by moving the particle from 1 to 2 by that force. So you'll generally get something like fx dx plus fy dy plus fz dz. And so you're going to be thinking, well, those are 3 independent sort of things, which is sometimes the case. But generally, we have to think about the fact that there is a path involved. And so the way that we handle that path is that the path itself can be written as a function. So if it's sort of an analytical path, that means that, for instance, y will be perhaps a function of x, or maybe z will be some function of x and y, whatever. If that's the case, then you need to also find dy as a function of dx and dz as a function of dx and dy, which you can further substitute to get dx. And then you'd have to perform these substitutions so that you would have a single integral here, where in the case that you did substitutions, everything would just be times a dx here after you've made your substitutions. Are you guys following that? Right. So that's the general gist of it. Or in the case of this one that went along that semicircular path, I was able to get my integral path to be down to something that depended on just one variable instead of two variables. All right. So once you've done that, you're going to do much better. And if you can't do that, that's fine. And there's, worst comes to worst, there's always numerical solutions and things like that. So even for non-analytical paths, we can always evaluate this thing. All right. So I think that we will go ahead and, is there anything else I need to say about that? Give me just a moment here. Where is Okay, I think that's all I got. Another thing that we left off with last time, if I remembered correctly, is that we did get work kinetic energy theorem. If I recall correctly. Yeah, we sure did. Okay. So we also last time were talking about work kinetic energy theorem. And so I'll start from there. All right, so the work kinetic energy theorem states that the final kinetic energy is equal to the initial kinetic energy plus the works done by all forces. I'll just say, okay. By the way, that should say final. Okay. And a lot of times we've seen conservation laws like this. We've seen them for momentum and angular momentum, and they were very useful, especially they were also still useful in the case that this term here, which was whatever provided the change in the variable, when that term was 0, we usually got useful results. But this time, in the case that the net external work is 0, then what we're left with is a statement of kinetic energy conservation. So the kinetic energy is conserved if the net work done on my system is 0. And this can happen in a couple of different conditions. It can happen when the net force on my system is 0. Just remembering that the work, the total work, is equal to the integral of the net force dot dr from initial to final. So in the case that no work was done, or in the case that as you move along that path, R1 and R2 are the same. So if delta R is 0, which as you move along a path is generally only possible in the case that delta T is 0, that type of thing. So really what we're getting here is that if the net force on something is 0, then the final kinetic energy equals the initial kinetic energy, and where masses are treated as constant, it just tells you the final speed is equal to the initial speed. We already had from Newton's second law that in that case, final velocity is equal to initial velocity, which is even more information than this thing's giving us anyway. So this is not, in general, useful as a conservation law. It's useful as work kinetic energy theorem. Sure, if there is a net force acting on it, then it's great. It tells you what happens to kinetic energy at all later times and stuff. That's really, really useful. But as a conservation law, it is not useful. Okay. So we will, maybe I should sum this up. So in that case, I'll say meaning V final equals V initial is what you wind up getting out of it, which we already knew. From Newton's second. So we'll just say that it's, work kinetic energy theorem is only useful for the cases where kinetic energy actually changes. Okay. Okay. So let's move on from the work kinetic energy theorem to, well, eventually we'd like to get to the work energy theorem, which would involve us having to get to energy, which means that we have to think about the fact that there's not just kinetic energy for mechanical systems, there will also be potential energy. Okay. So potential energy and conservative forces. The thing here is that conservative forces can have potential energies associated with them. That's something that, you're probably familiar with from your introductory courses. So let's say all conservative forces can have potential energies associated with them. Okay, so if we want to think about what are all the different types of potential energy, then we have to identify what are the conservative forces. So, forces. We generally like to express forces, as analytical expressions. So where they can be functions of location. They can be functions, in the case of the drag force, they were functions of velocity and speed. We could also have forces that are functions of time varying forces. And we can have forces that are functions of even more complicated things. All right. So what we want to think about here is that, if I want to identify what are conservative forces, what I need to know is that conservative forces cannot be functions of any of this other stuff. It has to only depend on R. It has to depend on R and R alone. So Let's just go ahead and cut to the chase. Conservative forces must meet two conditions. The first condition is that the force depends on location and location alone. So the force is equal to a function of location only, if that makes sense to you. Can't depend on any other thing except for location. Good examples would be the gravitational force. I can express the gravitational force on an object, lowercase m, located near an object that's the source of a gravitational force whose mass is capital M. So that force is equal to g capital M lowercase m over the distance between their centers squared in the negative r hat direction, meaning that it is attractive along the line that connects the two. So in order for this to be a conservative force, it looks like it's a conservative force. It depends on, there's something that's part of R, there's another part of R. This will only really be a conservative force if G and M are constants. Okay. So let's think about some recent ideas that have come up. Like, for instance, what if the gravitational constant was a function of time? Right? This is like the expansion models and things like that. Gravitational constant could be a function of time. What would that mean? That it's no longer a conservative force. That the potential energy associated with it would change with time. That the total energy of the universe would not be a constant quantity. And if we think of energy as stuff, indeed where did it come from? This leads to many, many questions. All of a sudden you're all the way out at the edge of science. And if indeed you could find that to be true, then energy conservation would not hold anymore, right? So that would be indeed a very interesting situation. But then you might say, well, what if it changed? And this is part of what astronomers are doing when they look so far back in time, right? Looking for this type of thing. Do you guys know what I'm talking about? Okay. So, the point is that we do have something called the law of conservation of energy as of right now. And we have such a law because it has never been observed to not be true, right? And you might say, well, what if things varied so slowly? Or what if it was a time that it was like this that we couldn't see? Now you're outside of science. If you're going to accept the idea that this is maybe a scientific idea, except that there's no way for us to find any evidence of it, then all of a sudden you're no longer discussing a scientific idea, right? All right, so it can get pretty nasty, and that's what I mean by you're all the way at the edge of science at that point. Okay. All right, but if this were the case, then the energy of the universe would not be a conserved quantity. And that's just not really a point related to the chapter, but I'm just going to put it on there anyway. And indeed, when we move past mechanics to quantum mechanics, the derivation of conservation of energy basically just follows from the idea that if there is a symmetry to the universe, that it doesn't matter where you are in time and the laws of physics will be the same, then energy must be a conserved quantity, because your Hamiltonian time have this unique relationship. Just like momentum and X have a unique relationship, and they show up in Heisenberg uncertainty principles, that's that unique relationship we're having, is if, doesn't matter what I call x equals 0, then P will be a conserved quantity. If it doesn't matter when I call T equals 0, then E will be a conserved quantity. That's the relationship. That's how you would derive conservation of energy in quantum mechanics. But today we're going to derive it in classical mechanics, which is actually harder. All right. Other forces that come to mind as conservative, as meeting this first condition would be the electrostatic force. That was K, Q. Let's have a source charge be capital Q, Q over R squared in the R hat direction, where now if one of these is negative and one's positive, it's attractive, and if they're both positive, it's repulsive. Another example would be the force from a spring, which has a magnitude of kx and acts in the negative x hat direction. Okay, that type of thing. All of those are going to be things that we, just again, like we did in your introductory physics course, we found potential energies could be associated with the gravitational field, with the electric, with the static electric field. If it weren't a static electric field, meaning if the field were a function of time, then we'd have a force that's a function of time that's no longer conservative. All right, so only for those static electric fields, and for a spring field. All right. A spring's not exactly a field, but force from a spring. All right. Now, what's that second condition? Oh, I should also point out that examples of forces that don't meet those conditions, the clearest one would be the friction force, but also the drag force, because they're functions of velocity. Force from me, pushing things, because I can have times and moods and all sorts of things. So, all right. All right, so the second condition for a conservative force. For any 2 points, 1 and 2, the work done by the force from moving point 1 to point 2 by the force is the same for all paths. So the second condition is for any 2 points, 1 and 2, the work when moved from location 1 to location 2, the work done by the force must be the same for all paths. And I'm using the upside down capital A to symbolize for all. That's going to happen whenever the word for all comes up. Okay. So let's go ahead and think about what that means. I have a work, a force that's maybe doing work as I move from location 1 to location 2. And I'll just remember my definition for work. F dot dr. Okay. And let's say that I moved, I want to go ahead and do a gravitational example, or, well, sure. Let's go ahead and do the gravitational example, I suppose. If I want to think about the work done by the force of gravity, I'm moving from a first location to a second location, then I need to think about, let's say I move from location 1 to location 2. And this is in the usual coordinate system. So I've got, I'm going to go ahead and let 1 be my origin. All right. And as I move along that path, like let's say I take the straight path first. So that's my path. At any moment along there, I can draw a free body diagram, and the only force acting will be the gravitational force in the downward direction. So the magnitude is mg, and the direction is expressed in the arrow. Okay, so there's my free body diagram. And as I move along, I need to calculate the integral from 1 to 2 of f dot dr. So I've got my integral from 1 to 2 of mg, and now I've got mg is in the negative y hat direction, dotted with the dr vector. All right, so I've got, I'm going to bring my mg out front. Integral from 1 to 2. And I've got y hat is down. dr is sort of this away, right, as I move along. So I've got, let's go ahead and call this angle here theta. So I have to think about a dot product between, you could do this a couple different ways. But I'm going to take it as the dot product between these two vectors, so the negative y hat and the dr direction. And what that's going to give me is the cosine of 90 degrees plus theta, times the magnitude of y hat, which is 1 because it's unit vector, times the magnitude of dr, which is the increment of length. Now that angle is also a constant, so it can come out front. And I've got mg, now cosine of 90 degrees plus theta. That is, let's go ahead and sort of imagine it. Some of you guys probably remember your trig identities, which is fine. Let's say that's theta. And this is 90 degrees plus theta. So the cosine of 90 degrees plus theta, well, look, it's a negative number, but it is equal to, in magnitude, to the sine of theta, but it's a negative number. So cosine of 90 degrees plus theta, I'll just remember, that's equal to negative sine of theta. And now I've just got my integral of dr from 1 to 2, which I took a straight path. So that's just going to be sort of a length of this path, L. Okay. So I've got minus mg times L sine theta. And L sine theta, I will notice, is equal to this side of this triangle, which is y2 minus y1. So minus mg delta y. That's the work done by gravity. Okay. So that's fine. But then I also notice, what if I did a different path? What if I walked, took my object along this way, where now there's the free body diagram, and then up this way. So that would be a second path. Well, as I walked along sideways, along the x-axis, what would be the work done by the gravitational force? 0. Because it's a dot product of f and dr, which everywhere involves being multiplied by the cosine of 90 degrees, which is 0. Are you all okay with that? Okay. And then as I go up here, I still have f and dr, where now f is down, dr is up, which is going to give me the magnitude of the first thing, which is force, which is mg, the magnitude of the second thing, which is this distance here, which is delta y, in terms of magnitude, times the cosine of the angle between them, which is 180 degrees, which is where that minus sign would come from. It doesn't matter what path you choose, you'll always get the same. So this tells you that the gravitational force does indeed have a sort of path independence. You're welcome to try more. So it meets condition 2. Whereas the friction force, the work done by a friction force and moving from 1 to 2, and now I'm not talking about space, I'm just talking about moving from this location to that location, the work that was done by the friction force as I did that. That will always be equal to, let's just go ahead and write down, f dot dl. And the friction force is always in a direction that is opposite to motion. So that is going to give me a magnitude of the first force, which will be friction force, which is not dependent on location or anything else. It's just, we can talk about this friction force here, which is dependent only on normal force. So that's not going to have any dependence during the time that I move it horizontally. And dl would just be the length of my path, and the cosine of the angle between them is always -1, because the angle between them is always 180 degrees, because as I move along a path like so, my motion is always along the dr direction, and my force is always the opposite direction. Okay? All right. So in that case, if I move from location 1 to location 2 like that, I do a certain amount of work. And if I move from location 1 to location 2 along a path that's like this, boom, much longer path, I did a different amount of work. All right? So clearly that cannot be a conservative force because it doesn't meet the second condition. All right. I think the horse is dead. So let's keep on trucking. If all the forces acting on a system are conservative, let's see what happens then. So this is going to be my approximation for just a little while now. All right. In that case, I have a potential energy associated with each of the forces acting on my system. If we want to just imagine that for the moment there's only one force acting on my system, then what I would have is I would have a potential energy also associated with that force. And your book is going to use the letter U for that potential energy associated with that force. And I just have one force acting, so I can just use one U. And that potential energy will turn out to be a function of location. So I'm going to go ahead and put its argument here. And the definition of the potential energy at that location is going to be the integral from wherever you're calling R naught, which would be sort of a reference location, where you're a place where you're saying, I'm going to let potential energy be 0 here. Then you take an integral from that location to the location that you're interested in of negative f of r dot dr. Okay, and that is going to be our definition of potential energy. Okay. And it's going to have the characteristics that we want, as will be illustrated shortly. Also, once we define potential energy, and in this case I again only have one force acting for the moment, then we can also define mechanical energy. And that will be equal to kinetic energy plus potential energy, or in the symbols of your author, kinetic energy plus potential energy will always be equal to mechanical energy. So this is our defining statement, our definition of mechanical energy. Okay. I want to do that example. All right, we're going to find the potential energy of a charge in a uniform electric field. I'm going to trust your author that this is necessary. So let's say I've got a uniform electric field, and I'm going to make kind of a different coordinate system. I usually do. I'm going to start from, for instance, point 1. Like before, when I started from point 1 and went to point 2 and found the work. Here, I'm just going to use this expression here. So I'm going to start from R naught and go to R. So I'm going to have this initial point be my reference point. All right. And I'm going to go ahead and make it the origin of my coordinate system too. And I'm going to say that everywhere on my page, imagine that there is a constant electric field. Its direction is always up along the page. Its magnitude is always some constant that I'll call E naught. And I'm going to go ahead and call the up direction x hat on my figure. In which case, x cross. I can still call that y hat. It just means that z hat is into the page. Okay. So in that case, let's go ahead and imagine moving from my reference point to some other point. And because it doesn't matter what path I take, because I'm solving for potential energy, obviously this is a conservative force, so it's not going to be path dependent. I'm just going to go ahead and take the straight path. I'm going to travel from R naught to R along a straight path. And I'm going to have, so here's my little charge that's moving along there. I'm going to let it be a positive charge. So the free body diagram for that charge will be like so. There will only be one force acting, and it will be the electrical force. Okay. And let's remember that the magnitude of the electric force is Q times E naught. All right. So let's use our expression from here. U of R is equal to minus the integral from R naught to R of F dot dr. Okay. So I've got minus the integral from R naught to R. F has a magnitude of Q E naught and a direction x hat, and dotting with dr. Again, I'm going to go ahead, doesn't really matter, I'll go ahead and make that theta. Okay, so I've got minus Q E naught. The integral from R naught to R, I want to evaluate this dot product. The magnitude of the first is 1 because it's unit vector. The magnitude of the second is dr's magnitude. And then the cosine of the angle between them is, let's see, the cosine of 90 degrees minus theta. You guys all right with that? Because this is the angle between the r hat vector and the force. This is theta. I think that's right. Okay. So now I've got minus Q E naught. This angle is constant, so I can pull that out front. Let's remember that cosine of 90 degrees minus theta is also known as the sine of theta. Oh, wait a second. Cosine 90 degrees minus theta. I think it's sine theta, isn't it? Let's go with sine theta. Okay, I'm just having this is a different derivation than I did in my notes. So, all right. And then I just have to integrate dr, the magnitude of dr, as I go from this point to that point, which I'll just go ahead and call that distance L. All right. And so what I have then is, I don't know, minus q e naught L sine theta, which would be delta x. Yeah, I believe that. Okay. All right. So I'm trying to remember if that's the same expression that your author got. Like I said, I wasn't. Let's check it. Chapter 4. I can't even find the example now. Oh, yeah, that's good. We got it right. Okay. Oh, except that x naught was 0 if your author uses x naught as 0. But okay. So this would be how you, in general, can calculate potential energy at some location. Are there any questions about that? So let's go ahead then and move on. Something that we generally use more than this is an expression not for u, but for delta u. And that's an important expression that I would like to find now. So I'm going to do that by noting that, let's say that you move from, that you're a conservative, a conservative force is acting, and you move from location R0 to R2. There will be a certain amount of work done by the conservative force. And it will be the same work that is done if you go instead from R0 to R1 and then to R2. Because, again, work done by conservative force is not path dependent. Are you okay with that? All right. So let's note that the work that I do when I go along this path must be equal to the work that I do when I go along that path. The work done by the conservative force. Not that I do, because I'm not conservative, but that a conservative force does. All right. I'm just going to be very clear that I'm only talking about a conservative force here. That's what CF is going to stand for. Is equal to the work done by that same conservative force, R0 to R1, plus the work done by the conservative force, R1 to R2. Okay. Now, if I want to get an expression for the work done by the conservative force going from R1 to R2, it must be equal to the work done by the conservative force going from R0 to R2 minus the work done by the conservative force going from R0 to R1. And now we can make a nice little substitution here. And we see that the work done by the conservative force and going from R1 to R2 is equal to, oh, that's negative the potential energy at R2. I'll remind you of that expression. Work is the integral of f dot dr. So where I see work, I notice that is just like potential energy, except it doesn't have this minus sign that it needs to have. So that's negative the potential energy at R2 minus, again, where I see work, negative the potential energy at R1, where now those are the potential energies associated with that conservative force. Negative U at R2 minus U at R1. Okay. And, you know, the way that we see this expression more is we see it as delta U is equal to the negative of the work done by the conservative force from R1 to R2. So yeah, it's nice to have that expression for the definition of potential energy at some location, but this will actually be the expression that we use more often. All right? So just note that this is a very useful expression. For delta U, for the change in potential energy. Okay. Meanwhile, I'm going to get to conservation of energy, so let's do it. Let's remember our work kinetic energy theorem. That's still just sitting there being true. The change in kinetic energy, well, I guess I'll write it the way I generally write it. T2 is equal to T1 plus the work done. And again, remember, I am still talking about the case where all the forces acting in my system are conservative. This is still part of that conversation, where I guessed for a little while that it would just be one force. That's fine, didn't have to be. But I'm still in that conversation. That's still holding. Meanwhile, for this system, T2 is equal to T1 plus the work done by, you know, as you move from R1 to R2, by all the forces acting, which in this case is just that one conservative force. So delta T is equal to positive work done by that conservative force from R1 to R2. All right? This line here only holds in the case where I have just this one conservative force acting, and that's the example I went to. So for this case, I see that delta U is equal to, well, I'll do it this way. Delta T is equal to the work done by the conservative force, which is equal to negative delta U. T final minus T initial is equal to negative U final minus U initial. T final plus U final is equal to T initial plus U initial, also known as E final equals E initial. So in the case that I only have a conservative force or multiple conservative forces acting, in that case, my final mechanical energy at any later time will be equal to whatever it was initially, at whatever time I chose to call T equals 0. This has a name. It is the conservation of energy. It only holds in that condition where only conservative forces are acting. And I think that's all we got for today. So we'll pick up with non-conservative forces on Friday. There is homework due Friday, and I'll return your old homeworks on Friday as well.